Okay, this is a lecture for my Math 310 course in ordinary differential equations. So this is not a comprehensive lecture about these topics. It's simply a review of some of the concepts from linear algebra that we'll be using in the Math 310 ordinary differential equations class. So just some basic notation and dealing with matrices and the properties of matrices. Okay, so the first thing we're going to do is just have the proper notation. We're going to write a matrix like this. It'll be denoted by a capital letter, which is typically in the textbook bold-faced. And then the matrix will consist of elements in the rows, and they will be labeled in this manner. So the first indice is indicating the row, and the second indice is indicating the column. So this is A21, second row, first column, and second row, second column, etc. Second row, nth column. Okay, so and then we would continue all the way down here, and then we would have the mth row, first column, mth row, second column, and then the element here in the bottom right, the mth row and the nth column. Okay, so it'll be an m by n matrix. So m is the first number is the number of rows, the second number the number of columns. So that is m rows and n columns. Okay. The elements in the matrix A, I, J are complex numbers. Complex numbers. Okay, so, and we may sometimes use a alternate notation just this way here for shorthand. Well, the matrix A containing the elements, all the possible A, I, J in their normal places. So in the text, this is sometimes boldface. Okay, we will refer to a column vector. So a column vector is a m by 1 matrix, and it consists basically of one column, looking like this: A1, 1, A 1, 2, all the way down to A1M. Okay. These are often in our textbook. This is often in boldface lowercase. Boldface lowercase. Okay, and similarly we can have a row vector. A row vector. A row vector is a 1 by n matrix. And it looks like this: A11, A12, dot dot dot, A1n. Okay. So that's our notation and how we're going to designate a matrix, a square, a rectangular array of numbers. Sometimes they're square, but not always. For equality, what does it mean for two matrices to be equal to one another? If we have matrix A designated with the elements A, I, J, and matrix B designated with the elements B, B, I, J, we will say that A is equal to B if A, I, J is equal to B, I, J for all I and J. Okay, this little symbol here like that means for all. Okay, we can add and subtract matrices. So A plus B means we take the two matrices denoted in this way, B, I, J, like that, and then we form the new matrix where each element is the sum of the equivalent elements in the same place in the other matrix. Okay, and similarly subtraction looks like this. Okay, so you simply subtract the elements that are in the same places and form a new matrix in that manner. Okay, we can also multiply by a scalar. That is a single number. So we will be taking a scalar, say a given, I'm going to call it alpha, given alpha in C. So that would be this little symbol here, C meaning a complex number. Okay, so then if I wish to multiply a matrix by a scalar, I could write it like this, and that will mean that every element in the matrix is multiplied by that scalar. Okay, and then just as a side note, -1 is a scalar, so note that then minus a means -1 times a, and that means that we would multiply each element in the matrix by the negative sign. Okay, next coming to the multiplication of matrices. This is slightly more complicated, and we have to be careful with the size requirements. So here we have A, and that this could be an M by N matrix, and we have another matrix B, which is of size N by R. Okay, these must match. This thing must be the same as this, otherwise you will not be able to multiply them together. So what I'm saying is we are multiplying an M by N matrix of size, we are multiplying by a matrix of size N by R, and these guys must be the same. Okay, and then the resulting matrix, when I multiply A by B, so I'm now thinking of myself, I'm multiplying AB, and this will be equal to some new matrix, let's call it C, and then the size of C is M by R. That is M by R. Okay, and the elements of C will look like this. Cij will be the sum from k equals 1 to n of Aij times Bkj. This is going to be much easier as seen as an example. So let's just quickly take an example so we can see that. What's going on? Here I'm going to multiply a matrix which is 2 by 3. There's the elements of it right there, 1, 0, 2. That's a 2 by 3 matrix. I will multiply it by a 3 by 2 matrix. You see that those inner dimensions are the same as required. There's some numbers in there. Okay, I'm going to multiply these together. That means I'm going to take, to form the element in the upper left corner of my resulting matrix, I'm going to take 2 times 0. I'm going to actually write it out here in longhand what I am doing. I'm taking what I would say, I'm taking the first row into the first column. So I'm going to go 2 times 0 plus 3 times 1 plus 4 times minus 2. That's going to be the element in the 1, 1 position in my C matrix. Okay, then for the next one, I will take the first row into the second column. So I'm thinking here of going 2 times 1 plus 3 times 0 plus 4 times 1. And then I do the next row into the first column. So I'm going to do the second row into the first column, and I'm getting 1 times 0 plus 0 times 1 plus 2 times minus 2. And then finally, the second row into the second column, and I'm getting 1 times 1 plus 0 times 0 plus 2 times 1. And if I don't make any arithmetic mistakes, what I believe I get out of this is minus 5. That would be 3 minus 8. So I get here minus 5, and then I get 6. Let's see, that would be 4 plus 2. I'll have 6. And then here I have 0, 0, and here I end up with a minus 4. And did I make a mistake there? Hang on a sec, let me check this. 1, the first one, 0, 2 times minus 2, 1, 0, 1. No, I think not. Minus 4, and then I'm going to go here, 2 times 1, 1 times 1, I get 3. Okay, so I multiply them. I try not to make any arithmetic mistakes. Okay, then we have a couple of properties about matrix multiplication, and we need to be cautious of one thing in particular, but let us just state the more straightforward ones first. If I take AB, the product AB, and I multiply it by the matrix C, then that is equal to A times the product of B and C. That means that matrix multiplication is associative. I can also distribute. That means if I take A and I multiply it by the sum of B plus C, then that will be equal to AB plus BC. That is distributive property. All right. However, let's be very cautious. AB is not equal to BA. So matrix multiplication is not commutative. This is different from regular numbers. It matters in which order you do the multiplication. So be careful about that. It's not commutative. All right. What else can we say about these things? There's an identity matrix. The identity matrix looks like this. We label it always with I, and it looks like this. 1, 0, all zeros. And then 0, 1, all zeros. And then we keep going down here, and finally we'll end up with zeros, and then there'll be the final one here. So this is the identity matrix. So it's basically all zeros except with ones on the principal diagonal. Okay, that's this thing here. So on the principal diagonal, there's all ones. It is the case that you can multiply on either side by the identity matrix, and nothing happens. Okay. Okay, inverse. And this is, let's be careful, we can take the inverse of a matrix, but this is for square matrices only, which is mostly what we're going to be dealing with. We're going to be dealing with systems of differential equations, and the coefficient matrices that we get will be square. Okay, so for square matrices only, we say that A is invertible, which means it has an inverse. A is invertible, and we have another word for that, non-singular. So A is invertible or non-singular if there exists, that's that nice little symbol there, means there exists some other matrix B such that AB equals BA equals I. Okay, so this is the same idea like that we would have, say, with numbers. For example, 2 has an multiplicative inverse of 1/2 because 2 times 1/2 equals 1, and 1 is the multiplicative identity. Okay, so this is exactly the same idea. We have the identity matrix with the position, with the type of property like 1 has when we're thinking about numbers, and when we multiply by 1, nothing happens. And we also we have the idea of the multiplicative inverse being what do we multiply something by in order to give the multiplicative identity. Okay. If we can find this B such that we can multiply A times B and get the multiplicative inverse, the identity matrix, then B is the inverse of A. Okay, and we say that B is called the inverse of A, and we write it like this, and B is equal to the inverse of A. Okay, we have a powerful statement coming, that is A is non-singular if and only if the determinant of A is non-zero. A is singular if and only if the determinant of A is equal to 0. Okay. I'm going to have to go a little bit further down here in my inverse category before doing the transpose. We can compute So you can compute the inverse using Gaussian elimination. Okay, so how do you do that? You take your matrix you wish to compute the inverse of A, you augment it with the identity matrix, you use Gaussian elimination until you have transformed the matrix you started with into what looks like the identity matrix and something else, and that something else will be the inverse. This is in our textbook for the course Boyce and DePrima, page 291. This happens, you can do this in O(n) cubed operations, where n is the size of the matrix. We have an n by n matrix. Okay, so if you can't remember how to do Gaussian elimination, review over that so that you can find a matrix inverse. Okay, we can also take the transpose of a matrix. And I'm in part G here, transpose. What we basically do, this is an interchange, the transpose is an interchange of the rows and columns. Okay, so if A is equal to this matrix, then A transpose, which I'm going to write like this with the little t up there, A transpose will be this one. You notice that the I and J have been swapped. Okay, let's just give a quick example. Imagine A is this matrix here, 1, 2, 3, 4, 5, 6. Then A transpose looks like this, 1, 2, 3, 4, 5, 6. The rows of A are the columns in A transpose. Okay, there's also a conjugate transpose, and that is also called the adjoint of A. So first, just before we talk about what's the conjugate transpose, let's just talk about what the conjugate is. So let's take a look at the conjugate matrix. So we have some matrix A, and the conjugate matrix will be written like this, A with a bar over it. Okay, where A, I, J in the elements in the conjugate matrix are the complex conjugates. Are the complex conjugates of A, I, J. Okay, just an example of a complex conjugate. If we have some number 1 plus 2i, and we take the conjugate, complex conjugate of it, that looks like this. Okay. So given A is equal to the matrix containing these elements is little a, I, j, then A conjugate is equal to that. Okay, quick example that for a matrix that would be, imagine I have this 2 by 2 matrix with complex entries looking like this. Like that, then I would write the complex the complex conjugate matrix looking like this. That would be minus 2i, and then this would be minus 1 minus 4i. This would be 2 plus I, and this would be 4. Right. So if that's what the conjugate matrix is. Now if we want to do the conjugate transpose, what we do is we take the conjugate and then we do the transpose. So let us now take our A conjugate and make its transpose. So A conjugate transpose will look like this. We will now take the transpose, and that will be the first row will become the first column. So that'll look like this. And then the second row will become the second column, looking like this. Okay, looks like that. And so we're basically doing both. We can do it in either order actually, but you basically take the conjugate and then do the transpose. And we write that like this: A conjugate transpose, we have another symbol for that, A with the star up there, like that. And that is called, this is called the adjoint of A. Okay, so some basic terminology and things we can do with matrices. I'm going to say a few other things, a bunch of things about vector multiplication. So we can think of vectors as 1 by n or n by 1 matrices. But right now, so now we're just thinking of a single row or a single column, and we can say some things about the multiplication of vectors. First one, okay. Dot product. Dot product. Okay, imagine I have two column vectors. There's A, x, 1, 2, and 3, and then my second column vector, y, being 4, 5, and 6. Okay, to take the dot product, what I do is I take x transpose and I multiply by y. So that looks like this, x transpose. That is going to be, well, it's a column vector, so it will become a row vector. It'll be this, and then it will be multiplied by y. And this is, well, it's done exactly the same way as the matrix multiplication. I take the first row into the first column, and that's all I have. So I do that computation. That would be 1 times 4 plus 2 times 5 plus 3 times 6. That comes out to a total of 32. Okay, and that is the way that I did that. That is the sum I equals 1 to n of xi, yi. Okay, next, so that's the dot product. Next thing is the scalar or inner product. And that's going to be denoted this way, like that. And that is going to be the sum from I equals 1 to n of xi times yi conjugate. Okay, where xy is x transpose y conjugate. Okay, so just be careful that we're going to make this distinction about whether or not we're taking the conjugate before doing the multiplication. So when the numbers are all real, when we have no complex numbers, so when the numbers are real in our vectors, are real, so that would be in R, then 1 is equal to 2. Okay? Then the dot product and scalar product and inner product are the same thing, but not when the numbers are complex. Okay, next point, x 1/2. Okay, so this is the square root of the inner product of the two of them. Okay, so that sometimes we denote that this way with the double bar on either side. That is the magnitude of x. This is the magnitude of x. Okay, basically how long it is. And so only the zero vector has length 0. Okay, if the inner product is equal to 0, then x and y are orthogonal. Okay, so something to just note here with this slight complications with the complex numbers in here, that x transpose x, which is equal to the sum of I equals 1 to n of xi squared, and this would be the dot product, may not be real. Okay, So therefore it is not a length. It is not a length. Plus, it may be 0 for non-zero vectors. So just a little bit of caution when using the complex numbers. Okay, so let's take an example. Let us imagine we have a vector x with the elements 1 and I, and then that would mean that x transpose would be 1 and I as a row vector. Then x conjugate transpose would be 1 and minus I. X conjugate would be 1 and minus I as a column vector. Okay, let's take a look at what happens. We can compute x transpose x, and we get the sum from I equals 1 to 2 of xi squared, and that will look like this: 1i multiplied by 1i, and we get I squared. Sorry, we don't get I squared, we get 1 squared plus I squared, and that is 0. However, the inner product, xx, is here the sum from I equals 1 to 2 of xi times xi transpose. Sorry, xi times xi conjugate. And that will be 1 times 1 plus I times minus I, and that will be equal to 2. It's different. This one is 0 and this one is 2. Okay, and then meanwhile then the magnitude of x will be this inner product, the square root of the inner product, and that's going to be square root 2. And that's telling us that if we put in the Argon plane where this thing is, it looks like this. There's this being the real axis here, the real axis here, and this being the imaginary axis up here. We could plot this thing, it's right here, 1 plus I, that's what we started with x, and then we see that this length right here is the square root of 2. Square root of 2 is the length. So that is our various flavors of vector multiplication. We have the dot product, and we're careful with, we've got the scalar or inner product as well. And sometimes they are equal and sometimes they are not. Okay, and so as we actually saw coming already in our last lecture, we saw that we can have matrices and vectors of functions. So the entries in our matrix can be a function. So this is something that may be new to you or not. Let me just make note of that. The entries in our matrices can be functions. They don't have to be numbers. We saw actually the complication that comes when we're talking about linear independence, and we have vectors that are vector functions. Okay. So when we have the entries in our matrices, especially for this course, the ordinary differential equations, typically the entries in our matrix are going to be the coefficient functions on our differential equations. So they are typically going to be functions of a single variable, and we often are going to be, the variable will also be real, and we often use t. Right? We're thinking possibly of a system that for which the independent variable is time. So I'm just going to note that. So typically of a real variable t. So we're going to have, for the purpose of this course, the matrix entries or the vector entries are going to be functions of a real single variable. Okay, here's an example of what that looks like. We could have the vector x. It is a function of t, and each one of these entries, x1 of, that's not an I, that's a 1, x1 of t, x happy with that. Let's just scrunch that out. x1 of t, x2 of t, all the way down to how many of them we have, xn of t. Okay? Well, that's what our column vector looks like when each entry in the column is a function of t. And similarly, we can have a matrix, A of t, and each one of the entries in the matrix is a function of t. So that's there, all the way across to a1n of t, and then coming down this way, am1 of t, etc., all the way across here to amn. Let me just reiterate, for the most part, we're going to be dealing with square matrices, but it of course doesn't. You can have a matrix of functions of which is not square. Okay, well, continuity. We are going to say that that a vector or a matrix, either which are functions of t, we're gonna call those continuous. We're going to say that is continuous on an interval I if every, this is important, every component xi of t or aij of t is continuous on I. Okay, don't confuse this with the identity matrix. I can see that a little bit notation can be slightly confusing. We have been referring to most of our intervals as I, but we also use I for the identity matrix, but context should tell you which one that it is. Okay, so we have a statement about what it means for these things to be continuous. Similarly, we can define the derivative and integral of a matrix or a vector function. So let's do that. Similarly, we can define the derivative or integral of a matrix or vector function. Okay, so we would write that as a sort of normal notation. We would say the derivative of my matrix A with respect to time. What do I mean by that? Well, that's the derivative of A, each element of the matrix. So I just go through the matrix, all the functions, I take the derivative of each one, and then that would be the derivative of the whole matrix. Similarly, the integral from A to B of my matrix is the matrix consisting of the integral of each one of the elements. Okay, let's take an example. It potentially looks a little bit confusing like that, but I think once we see an example, it's pretty straightforward. Let us take a 2 by 2 matrix of a single variable t, real variable. There it is. Okay, there's a matrix A. You can see it's a 2 by 2 matrix. There's 4 elements. Each element is a different function of t. Then we can take the derivative of this, and we will get the following. Okay. We simply take the derivative of each element. The derivative of t is 1. The derivative of t squared is 2t. The derivative of t cubed is 3t squared. The derivative of t to the 4 is 4t cubed. So that is the derivative of the matrix A. And the integral of the matrix A is similarly, we take a look at A and we integrate each one of the functions in it, putting them in the appropriate places. So let us take first the integral of t, that is 1/2 t squared. Then we take the integral of t squared, that is 1/3 t cubed. Then we take the integral of t cubed, we get 1/4 t to the 4. We take the integral of t to the 4 and we get 1/5 t to the 5. Okay, so we just go element by element, doing something that you already know how to do. Okay, just a few final comments. If we take the derivative with respect to t of c times a, like that, where c is a constant matrix, so let's identify that. C is a constant matrix. Well, that's a matrix just filled with numbers only. Then, if I in the same way that if I take the derivative of a constant times a function, it's the constant times the derivative of the function. It works exactly the same way. So that will be equal to the constant times the derivative of a with respect to t. Okay, but not dA by dt times c. That's because the matrix multiplication is not commutative. So be careful. This wouldn't matter if we were working simply with just functions and constants. We would be able to do it either way, but not. So just let me reiterate: matrix multiplication not commutative. So you have to keep things in the appropriate order. Okay, if I was to take the derivative of the product of two matrices, so C is a constant matrix, B is going to be a matrix of functions, like A. So A and B are sort of the same idea, both matrices of functions of the independent variable t. So I'm going to take the derivative of A plus b, then that is simply the derivative of this. I take the derivative of a plus b, I will see that as derivative of a plus the derivative of b. Okay, and then finally I will take the derivative of a product of those two matrices, and I will employ the product rule. Okay, so that will be a times the derivative of b with respect to t plus the derivative of a with respect to t times b. Again, order is super important. You cannot write these things in a random type ordering. It has to be a times the derivative of b and the derivative of a times b. Okay, so I'm going to put here, but not db by dt times a, or b times dA by dt. Okay, this is that same thing. Matrix multiplication not commutative. So be aware of that one and be aware of that one when you're doing this. You have to be much more careful keeping the ordering the way it is supposed to be because of that property of matrix multiplication. All right, that is all for section 7.2 of Boyce and DePrima, the review, the types of things that we're going to need as we solve systems of differential equations. Thank you.